first of all, continuous time system. Now, we will have a system. We have learned about phase. We have learned about response of the system, and we try to learn about the time and frequency relationship beforehand. And now we will have some practice. Now we are in practice. In most of the example we have learned by far is differential equation. So assume that we have this is our differential equation we want to solve. So someone may ask you, what is the impulse response to the system? So first of all, people may ask, what is impulse response? Some may ask, what is step response? Well, that's very popularly known. So what this one says here is, when you apply an impulse, basically a delta function to the system, what will be their output? What will be the output of the system when you apply delta function? 앞으로는 이름을 불러서 물어봐야 될 것 같은데. So if you say we have a system having a transfer function ht, when you apply a delta function as an input to the system, what will be output of the system? We have learned about this one many times. So I changed the name a little bit. We keep on use a system response. Okay. So we have used the name of system response, but this one is also called as impulse response. If you apply impulse, then there will be the system response come out. So if someone asks you, what is impulse response? Then it's same to find the system response, ht or hj omega, which is in frequency domain signal. Step response is when you have a step response ht, you apply a step, basically unit function, and what will be the output? That's the system, the step response. So let's do it one by one. To calculate the impulse response, we have to calculate h, the transfer function. So how we do it? In Fourier transform, we have learned that. Let's change this one to time frequency domain, and this differentiation, when you change this differentiation in continuous time, it will be j omega or 1 over j omega. This one? This one? I don't know. I don't know. Okay, this one I don't know. So this one or this one? Differentiation, which one's one? One, right? So j omega y, and there will be tau plus y, which will be x. That's how we change to Fourier transform. And then if you rearrange this one so that transfer function is what? The relationship between input and output. That's the transfer function. So the relationship between input and output will be this over 1. That's our transfer function, which you can show in here, over here. So this is our transfer function. So if you are asked to find the impulse response in frequency domain, that is your answer. If you are asked to find impulse response in time domain, then you have to do the inverse Fourier transform of this. If you remember and there will be, the result will be, I think tau 1 E minus tau T ut. Is it? Okay, no. Because if we take out the Fourier transform, keep in mind about this. That's over here. So if you remember the Fourier transform, that's over here. So if you have E minus AT UT, they becomes like that. A times J omega over 1. That's our basic principle. So in here, we change this one to be tau over 1 J omega plus 1 divided by tau. You can do that, right? And then if you see the relationship, tau over 1 is constant over here. J omega is still J omega. A corresponds to 1 divided by tau, which goes to here. That's our response. So this is our system response or impulse response, responding to the impulse with zeta function in frequency domain. This is our impulse response in time domain. And in case of step response, keep in mind, let's go back to the basic. I think you may forget many things, but let's go back to the basic. When you have input, any arbitrary input to the system, and inputs, the system has system response HT. What will be their output? Convolution, right? And also in frequency domain, convolution changed to be multiplication. That's the basic thing. That's the very basic thing we have learned before. So if you want to calculate output of the system when UT is applied, then that will be the output will be input, which is UT, convolution of our system response, which is this, right? So we do the UT convolution times tau over 1 E minus tau divided by T minus divided by tau UT. We do the convolution over here. And intuitively speaking, how you do the convolution? In convolution, you have time domain, you plot two signals, first of all, let's plot this one, which is typically given like that. And this is 0, which is tau over 1 e minus t minus tau. So it looks like that. And this one, we flip it. We flip it. And initially it looks like this, ut, but we flip it. And maximum over here will be certain value, let's say a. And let's move this one from the bottom until they become overlapping. And they begin to calculate those overlapping area. That's how you calculate. This is relatively simple because if you have certain value a, then they are not zero from a, and this one is 1. So we just simply calculate this one over one period, and over from 0 to a. That's what you can see over here. Because we are integrating from 0 to certain value. And if you plot it in time domain, as I said, they're decaying. In case of system response, which is impulse response, if you plot it, they're starting from 1 divided by tau, go down like that. When t is tau, they were given by 1 divided by tau e. There's a value like that. If you plot a step response, they will be given like this. They are reaching 0, they are reaching 1. When time of tau, there will be value like this. And this tau, we know that we often call them as time constant. That's how the system we have learned before. So in summary, if you want to know the system response, so I think we keep on talking about this one many times by far. If you know your system, first thing you have to know is what is your system. The way you know your system is finding system response, which is we apply the impulse, if you apply step function, and find out what is your output. That's your system response. And then, from using this system response, you can either do convolution or you can either do the multiplication in frequency domain to find any arbitrary output. According to arbitrary input, you can find any output. And one way you can find it here is, one example is if you apply unit step as an input and find what is the output, corresponding output. That's the step response that we talk about. So I think you may see some of the equation in other classes beforehand, but this is how we derive it. From using our Fourier transform, our the knowledge about the linear time invariant system, the knowledge about step response, and knowledge about impulse response or system response. That's how we initially derive it. But we just know we have used this result in other lectures beforehand. Okay, questions? Nope. So let's use it in both plot. So we only use the impulse response. So let's leave step response for a minute and use the impulse response. The result of impulse response is this. This is our impulse response. So let's think about some border plot. In border plot is what? We calculate phase and magnitude individually and plot it. So in border plot, if in magnitude in border plot, we put absolute value of system response, and then we put log 10, put 20. That's our both plot. To get amplitude of both plot. What is amplitude of this? What is absolute value of h? Right? So the numerator is 1. The numerator will be, let's see, square omega tau square plus 1. That's our amplitude. Because this is real, this is complex, so we calculate like that. And then we put it here, 20 log 10, 1 divided by root omega tau square plus 1. Remember, this log is actually half in power, and we can take that out. So then we can calculate. It will look like this. So, and then one more step here is, so now this 20 changed to 10 because we take out this half log 10, and 1 divided by something like this, we can take minus out because there is a minus 1 over here. You can take that out and make omega tau square plus 1 to numerator. Question? Yeah. Yeah, sure. So in here, when you put it in the system like that, I'll leave that and then I'll repeat over here. 20 log 10 root omega tau square plus over 1 like this. If you rewrite this part, you can think them as omega tau t plus 1 half, right? And there is 1, we can change it to, let's put minus over here, and you can make them the other side, right? So if you take out minus half to outside, 20 multiply minus half over minus 10. So that's how we calculate by far. So this is our magnitude. And we know that they will look like this. But why? Of course, you can plot in MATLAB. If you want. But why they look like this? So we will repeat it one more time. If you see this magnitude first, what we usually does here is we take two extreme cases. First of all, if you see here, omega tau and 1 are major kind of variables over here. If omega tau is much smaller than 1, that's one extreme case. Another extreme case is omega tau is much bigger than 1. There's no two extremes, right? In this case, if you see this part, if omega tau is much smaller than 1, then this value is much smaller than 1. So we can ignore this part. The total value over here, the yellow will be 1, right? If omega tau is much larger than 1, then this is much bigger than 1. So we can ignore this part. So the value in yellow will be omega tau squared. Right? So, if you, in this case, which inside this log is 1, then this whole value will be 0. So, our magnitude will be 0. In this case, the total value over here is omega tau squared. So, power of 2. So, there will be minus 10 log 10 omega tau squared. And then, why not take out this 2 to front side? So, there will be 20. It looks like this. So this is how we see over here 0 when tau is much smaller than 1, and in case that tau omega is much larger than 1, we have this. In between and in here we can think them like that, because in here they are same to log 10 omega minus 20 log 10 omega. Tau. You can think them like that. So if you plot it in this case, which is magnitude 0 and magnitude 0, it looks like this. Of course, so when magnitude is 0, that means they are starting from 0. But remember, this is log value. This is log value. 0 in log value does not mean that the actual value is 0. Actual value is 1. Right? So keep in mind about that. So they're starting from 0. Then eventually, then they began to decrease. This is frequency. In case of this, tau is kind of constant. Right? So they decrease by certain slope, which we have learned by what? Decade. 3 dB per decade. Decade is what? Decade is 10. Is it? Really? Why does 3 dB per decade come out? So, what you can see over here, the equation over here is, which is kind of constant. Of course, this is extreme case, but we know that they will decrease like that. And they will decrease by 3 dB per decade. Decade is what? 10? Really? Why does 3 come out? Where does 3 come out? What is octave? Octave is 12. I think all of you know that it's 3 dB per decade, but I think not many of you have thought about why the 3. Right? So basically, answer is over here. So, how to say? By oscillatory approximation, we know that the slope is 20 dB per decade. That's why you know it from this one. So when this one increased by 10 times, from 1 to 10, then they decrease by 2. 10 to 100 increase by the decade means here is they increase by like that. If they increase from 10 to 100, then they will increase like that. However, what we talk about here is why we talk about 3 dB. 3 dB comes from the fact that we always talk about root 2. So say that the peak value is 1. We try to find the point that they reach 1 divided by root 2. Right? And log of root 2, log 10 of root 2, and we add 20 over here. Because our system is given as, starting from the fact that 20 log 10 like that. So this one means that the actual magnitude changed from value of 1, which is over here, value of 1, to, so actual value over here is 1, actual value over here is 1 divided 2. The ratio difference will be given as minus in log. But as this log of this one is 0, so minus, we will not be concerned for this case. We only care about this part. And the value will be given like this, actually. But likewise, when we did before, 20 log 10, 2, and they will be given like this. If you take that out, there will be minus 10 log 2, which is, if you calculate, there will be 3. Roughly 363. That's the reason we talk about 3 dB. So, I keep on, but nobody raise a question because I keep on saying, okay, they decrease by 3 dB per decade. So 3 dB sounds very familiar to you, right? So nobody raised a question, but actually they are decreased by 20 dB per decade. Decade is, you're right. When I ask you what is a decade, some of you say 10. That's right. When you increase by 10, then they decrease by 20 dB. So 20 dB decrease, 20 dB decrease by decade is correct. It's correct. I intentionally put 3 to make you confused because 3 sounds very familiar, right? 3 sounds very familiar. You have to hear about that in very many cases. 3 dB, those 3 dB is when you calculate your bandwidth. So 3D comes from the fact that it's root 2 times smaller than the peak value. From peak value, they are root 2 times smaller. This point is 3 dB smaller, not the slope. They just say 3 dB smaller than the maximum value based on this calculation. Then this one is called as bandwidth. That's how we are familiar with the 3. But actually, the decreased slope is not 3 dB per decade. They are 20 dB per decade. So 3 dB is maximum to 1 divided by root 2 when defining the bandwidth. And then the slope, those decreased slope, is 20 dB per decade. But assumption here is, I think I'm talking too much, but assumption here is this 0 is assume that this omega t is much smaller than tau. Omega tau is much smaller than 1. So they are valid for these very small cases. This assumption, we talk about that omega tau is much larger than 1. So they are valid for large value. In between, we don't know. Because in between, they are given like this, which we did not simplify it. So this area is 0. Larger than this, they will slope like that. But between them, they slope like this, not a straight line. Those one, they follows this one. So that's the, in summary, in first order system, this is something called first order system because we have in J omega, they are powered by 1, not by 2. We will talk about second order system later. As they are powered by 1, this is first order system, and you may hear that, okay, in our bandwidth, they will be given by 3 dB point, and their slope decreasing by 20 dB per decade. If you will see that in later time, if you have second order system, so J omega square tau plus 1 over 1, something like this, they decrease by 40 dB per decade actually. Why? Because you have, let me draw in yellow. You have like this before, but when this is 1, but as this is 2, they will power 4. Right? Because there will be omega square tau square something like this. So it will be omega tau 2 something like this. Right? So when you take to this assumption, there will be omega 4 tau or something, I don't remember. And then this 2 omega power of 2 makes 20. Omega power of 4 makes 40. Because 2 in here will come out as in front side, which is 20 now. Now this 4 come out as is doubled. That's the reason we will have 40 dB instead of 20 dB if you have a second order system. If you have a third order system, it will be 60. So don't misjudge that. The slope is always 20. That's just for the first order system. Second order system, third order system, there will be sharper drop. What happened in a both plot in magnitude. In case of phase, what happens? In case of phase, before we move on, I will erase this one. So, Christian, before you erase it. Nope. So this is magnitude, and we have not carefully considered phase by far. But let's think about the phase now. In case of phase, let's take a phase of this one. So 1 divided by J omega tau plus 1, that is the phase of it. You can find the phase from our basic assumption Euler equation. So let's divide this one into 2. The numerator is 1, which doesn't have any phase because it's real. In denominator, they are J omega tau plus 1. From this assumption, cosine theta corresponds to 1, sine theta corresponds to omega tau. So from here, you can calculate tangent theta, which is given by omega tau divided by 1. Is it right? So to calculate theta, you do the arctangent omega tau. Come on. Omega tau like this, is it? So where minus? Where is our minus? Okay. Actually, you're right. So, one more time. Tangent theta is over here. In case of here, our tangent theta is, as I said, omega tau. However, if you combine as a system, so in here the theta is tangent inverse of omega tau. So I told you, I sometimes told wrong things to catch you are following or not. So in here, this is right, but remember, this is denominator, not numerator. So if you have phase of 0 on top, phase of theta at the bottom, they should be minus theta, right? Okay, so instead of angle. So the total, the whole system's phase of H will be minus theta, as you say, which is minus tangent omega tau. That's what you see over here. And this one, let's do the same thing. Let's say omega tau is much smaller than 1, then it's very small. Then omega is very small. Then this one is almost negligible. So tangent theta equals very small value, almost 0. That means the cosine theta will be 0. If the value is much bigger, the omega is become value, very large value, likewise what you can see over here, very large value, then omega tau is very big value, which may go to infinite. Then tangent theta equals close to infinite. Theta is what? Pi divided by 2. So we have minus over here, so it will be minus pi divided by 2. Then we begin to draw it. So in case of phase, similar to our magnitude, but it's slightly different, more complex than like that. In frequency, in frequency, this is phase. When the omega tau over here is very small value, then theta is close to 0. So they're starting from 0. When this omega tau is a very big value, almost close to infinite, the tangent theta of the theta in tangent theta will probably close to pi divided by 2. We have minus in front, so they will close to minus pi divided by 2. So they reach minus pi divided by 2 when omega is very big. In between, just follow this one. Just follow like that. And we usually pick a value at omega equals 1 divided by tau, which is 1. What is theta when tangent theta equals 1? What is theta? Right? And we have, don't forget the minus. That's the reason in your circuits, in your dynamics, you may see that, okay, they start from 0, they go to divided by 2. Once you may have that, you have, in case of control even, you may hear that you have a pole at the numerator. That means they decrease by pi divided by half, and at certain value, they will be pi divided by 4. You may already learn the logic, but this is how things are derived. We're starting from this one, coming from our impulse response, and say that we calculate our phase, and our phase, when this one is very small, there will be 1. This very big, there will be pi divided by half of the pi, and there's minus over here. They divide by half of the pi, and then At this point, certain point, there will be looks like that. That's the board plot. Question. And I think nobody here that the slope in phase, because in here is hard to calculate. So before we move, our speed up from now on. So before we move on, questions. Okay. So let's utilize this one a little bit. Let's change to second order system. Second order system you often see from the mechanical system having spring, damper, mass, and you may be familiar with this. In case of circuit, you have a voltage, resistor, capacitor, inductor, and there's a current flowing that. In both of them, they are very, very, very similar. So let's draw this one first. In case of you have a spring, mass, damper, where's my chalk? Say you have a spring, damper, mass. I think we already mentioned that. They were given by mx double dot bx dot plus kx equals the force. That's typically what you see here. If you have circuit, inductor and capacitor, the total voltage over here, if you flow the current in here, resistor, they will multiply the current. In case of capacitor, what is it? Integration of the current, integration of current divided by the C. That will be the voltage. It's a charge. And in case of inductor, what happens? I think some of you take my lecture took this one already. So they have this relationship. So in case of mechatronics, when you bridge mechanical and electrical system, mass corresponds to inductor, damper consumes the energy, resistor consumes the energy, so they are matched. Spring constant, which stores the energy in kinetic way, they store a corresponding to capacitor. And force giving an actuation of the system is same to the voltage in electric system. Displacement, which usually output of the system, is same to our current. So that's mechatronics. In mechatronics, we talk about that. Okay, mass corresponding to our inductor, resistor corresponding to our damper, voltage corresponding to our force. That's how the relationship goes. However, what you can see from here is you can see several simple things. It's given by, so assuming that this is basic variable, one-time differentiation, two-time differentiation, so given by second order differential equation like that. So we can model them as, okay, plus square dy dt plus y equals x. Because as I said, this one is more like an input to the system, which is corresponding to x. This and this is more like output of the system is corresponding to y. And if you divide by m, if you divide by L, then there is some constant over here. So we put the constant like 2 pi omega n. And in here, we define omega n square. And in here, we define anyways. So in case of the mechanical system, this omega n will be k divided by m, right, from this relationship. In case of this electrical system, they will be given by 1 divided by LC. It looks familiar, right? So you say, okay, our resonant frequency will be like that. Our resonant frequency of the circuit like this. So they are all related like that. In case of here, the chi over here is same to chi over here is same to B divided by M from here, or R divided by L divided by 2 omega n over 1. So 2 omega n over 1, that's a chi over here. And in case of here, B divided by M times resonant frequency over here, which is 2 times K, which is same to 2 root Km over B. And if you know the dynamics, it's familiar. If you have circuit R times 2 square 1 divided by square LC over 1, which is same to the fact that R times half C over L. That will be in case of circuit. But so this one defines this one relates the damping and the spin constant and mass together. This is more depending on the spin constant and mass. If you have a damping, actually this one changed a little bit, but let's neglect it for a while. However, what I'm saying here now is this one is modeled. This one is modeled in the way that we can calculate the output. So now we can consider this whole system to Fourier transform. So when you do the Fourier transform of this, then square 2-time differential equation is what? J omega square y. In here, there is some constant, which is constant over here, times J omega y. Plus, there is a constant, another constant, y equals some other constant, x. So if you solve it, the transfer function h, which is x over y, will form that j omega square plus some constant, which is over here, 2 omega n j omega plus some constant over some constant. That's it. That's the relationship you have it. When you compare this one to a previous case, we have 2 now. We have power 2 now. So you can do the same things. When this, we can either make them, now this is our relationship. If this one, this denominator happen to be formed like this one happen to be 1, chi happen to be 1, 2 omega n square form like that, you can change it to like this, and you have, this is your system response. in other cases, you can divide them into two cases, and then you do reverse Fourier transform individually. That's how you calculate their system response in second order system. When you plot it, I was mentioned that you have to plot in frequent domain, you have to plot in time domain to see how things are different. If you plot it, this border plot, you may see it. Using the same method, when tau omega is very small, then will be close to 0, and then they force down. Remember, this is not 2 dB, 20 dB per decade, it's 40 dB per decade because it's second order system. And you may hear that when chi is small, that means the low damping will have those rise. If chi is large, which is over damping, will have a flat like this. Corresponding phase, they change from 0 to y. Previous case, they changed to half of the pi. Now they have changed to pi, y. Because this is second order system. So, if you have phase, previously in phase, Fourier phase, you use Euler function. Right? So from here, we calculate that theta will be tangent inverse of, only to numerator, tangent inverse of omega tau. That's what we calculate. Of course, if you calculate whole system, there will be minus over here. In this case, even though you make this omega 0 large, then there will be tangent inverse j omega square. There will be a tangent, is it? No? No. Because in here, this is 2. So we have 2 times chi omega jn plus 1 minus omega square. That's what we have here. So in our tangent setup will be 1 minus omega square divided by 2 chi omega n. Omega. That's what you said. So in case of here, when you make omega very large, then this one will be neglectable, and there will be omega square divided by omega ratio depending on omega. Therefore, if you have this relationship, then this one is not only goes to infinite, however, they go to 2 pi because they go to 0. Because one of them goes to 0. Therefore, we will have the second order system makes you can think it this way. Second order system, they can be, how to say, if you see them more easily, in second order system, in second order system, you may see they have a relationship like this, and then you can think them as multiplication of two systems having a constant like that. This is possible, right? You have two second order system, you can divide them into two first order system. This one reduced by pi by half. So phase of this one, the first order system, they divide by pi divided by 2. Second half, first of the system, they divide by half like that. In case of phase, keep in mind E, J, theta range. If the first system has theta 1 phase, second system has theta 2 phase, then the total system will be theta 1 plus theta 2. So if you have two systems in series, when they multiply in frequency, their phase is actually added up. So the second order system, we can divide them into two first order systems. Each of them drop by half of pi. So if you add them together, in total they divide by minus pi. That's the reason that it looks like they change from 0 to minus pi instead of 2 pi. Because this one, you can think them as two systems. System. So by far, question before we move on.
오메가 n 제곱, 그러니까 스쿼어서 여기 식에는 그러니까 x 앞에도 오메가 n 제곱이라고 돼 있는데 사실 이 식을 세워보면 저기 n분의 1이 딱 되는데 이게
틀린 것 같아요. 확인해 볼게요. So question will be this part, which I will check it. It doesn't make sense to me also. So question will be, this is omega n. That not looks right. So I think there's typo. So I will check it later. Other than that. So in short, if you have first order, so you may see that if you want to draw a border plot, in case of amplitude, amplitude of certain things. If you may see that h is happen to be 1 divided by some function, like 1 divided by tau omega, something like this. How we calculate their amplitude? In amplitude, which is basically log, because there's log, we calculate the amplitude of this part minus amplitude of this part. If numerator is 0, 1, then its log will be 0, minus the log of denominator, which is 20 log 10 of this denominator. So eventually, there's actually putting minus in denominator. In case of phase, we use the fact that in case of the Euler formula, if you have first system theta 1, second system theta 2, this one result will be theta 1 plus theta 2, meaning that our phase will be addition of each system. If you have something like this, then there will be subtraction because the numerator will be have some phase, denominator some phase. That means total phase will be theta 1 minus theta 2. So in this case, if you have top, which is zero phase, bottom has some phase, we use the fact that similarly, zero phase minus phase at the bottom, eventually they will become minus phase at the bottom. So what this one says here is, because of the increase of magnitude, as we are using log, that's what we show here. In case of rational function, 유리함수 in Korean, rational functions having p and q like that, we can use previously learned both plots, meaning that, for example, in case of this example, shown on the graph, as we are using log, we are not comparing the amplitude itself. We are using log. Because of it, we have 1 at the top, h at the bottom, and we subtract those amplitude because our amplitude is log. Our phase, not log, but because of the property in Euler formula, if you multiply two systems, for example, their phase will be added together. If you divide two systems, their phase will be subtracted. So if you have something like that, we don't know that you don't have to calculate whole system, because if you calculate this system, if you already calculate this system, then this minus this divided by this will be magnitude wise 0 minus the numerator value, which becomes minus like this. Phase wise 0 degree minus phase in here, therefore 0 minus bottom phase at the bottom, which is minus phase at the bottom, which is what you can see over here. Also, if you have more complex system like that, if you want to take a water plot of it, of course you can make omega very small, omega very large, and begin to plot it. But you can simplify it because in case of that, in case of this one, let's have there is a 2 times of the whole system. Then, and assume that omega will be looks like this. So if you compare the system over there and system over here, I think I'm missing hat in here. You can see that there will be omega n, j omega, 2 chi omega n square, except there is 2 in front. If you have 2 in front, what happens? In case of magnitude, we are losing log. So that looks like, okay, 2 times the h, which we already know what is the water plot. If you want to know its magnitude, it will look like 20 log 2 plus 20 log h. This is what we already know. And this is what we added in here. So, in case of magnitude, we have the original one we already know about, over here. We just add this value. So, the whole, assume that this is our this h shape looks like. We just add them so that they shift it up. That's how we calculate. In case of phase is what? In case of phase of 2h does not change, right? No phase difference, because this 2 is a real number, does not have any degree inside. So this one can be numeralized as 2 delta 0 degree. So multiplication will be, so phase will be added, but 0 phase is added, so same to the phase of h. So it doesn't change. So what this one says over here is, if in case of a rational function, you don't have to calculate all Bode plot from the basic. If you know one Bode plot, you can either take the minus, plus, or divide them to for example, like if you have a second order system, you can divide them to 2 first order system, add the phase, add the amplitude in log, or if you have constant multiplication of the system, the phase does not change, amplitude shift to the upper side, or if you divide by constant value, they shift to downside. That's how we calculate both phase, both plot, without doing all the calculations. So in discrete time, we mentioned that we do not use both plot much because it doesn't have much meaning because they're repeating. But in case of discrete time, likewise, we have, if you are asked to find the impulse response, that means you will calculate its system response and do the reverse Fourier transform to find the system response. And then if you are asked to find the system response, you do the same thing. In system response, you already find the system response, do the convolution by unit input to find the output. That's quite similar in case of discrete signal. When you plot it, when you plot its phase and amplitude, as I said, they are, in case of discrete time Fourier transform, they are continuous in frequency and periodic in frequency. So they keep on repeating. This is repeating, and phase is also repeating by 2 pi period. So it does not have much meaning when you draw the both plot in discrete time Fourier transform.